All right, as for today, we're going to finish up chapter 5, part 1. And then that will be everything for the quiz. So then next class, we are starting chapter 5, part 2. So we're going to lecture that, which will not be on the quiz. And then actually next week, so on Tuesday, it's just a free day, activity day, any questions you have. And then we have our quiz. All right. So I'd like to give everyone like a lot of time, like we don't have too many free days in here. So just so you're aware, but I like the first one, want to start everyone on a good foot, like nice confidence. So if you have any questions on Tuesday, I mean, I won't be doing like anything. I might note a couple of things, 5 minutes, but that's basically it for there. Do we have any questions so far? Have we at least got started? Has everyone at least kind of got started? Yeah, to some degree. Okay. All right. As for today, so the big thing in Trig is we compute all these angles, but they're based on the two most common triangles, all right, that exist. One is the isosceles triangle, and there's only 3 types of triangles when we're talking shapes. Isosceles, and then what are the other 2? So isosceles means equal sides, 2 equal sides. What's the other type of triangles? When all sides are the same, what kind of triangle? What's that called? Equilateral. Equilateral triangle. And then when all 3 sides are different. Remember? Scalene. Right? See. So in Trig, we keep coming back to all that geometry, right? I mean, that's why math is so beautiful, right? So we're learning all this new stuff in Trig. You have to keep remembering all the stuff you previously learned. Math builds on itself. And so that's why I don't have to give cumulative tests, because all math is cumulative. You just keep getting to remember. All right, so I have an isosceles triangle. And this is a isosceles right triangle. If, all right, the sum of all angles inside a triangle sum to what value?
180.
What is it? 180, yes. All right, so if that guy's 90 and an isosceles triangle has equal sides, they also have equal angles, which means both these angles are 45 degrees. All right, and this is one of the most common triangles there is. Then, all right, I want to set up, because I'm going to find all the trig functions, I need to identify this missing side. And what magical theorem do we get to use?
Pythagorean.
Pythagorean theorem. All right, 1 squared plus 1 squared equals h squared. So hence h equals root 2. From that, I can then find the exact values of each trigonometric function for pi over 4 radians, aka 45 degrees. All right, because pi over 4, 45 degrees is pi over 4, that's pi over 4, 90 degrees is pi over 2, pi over 4 plus pi over 4 plus pi over 2 is pi. All right, which is 180 degrees. All right, so just we want to keep getting familiar with radians. And notice I have all these written in radians because that's what we use the most. So, but I know it takes time to transition from degrees, which we've been talking about forever, all right, to radians. All right, so sine, cosine, and tangent. What's our little acronym?
SOHCAHTOA.
SOHCAHTOA. So, ka, toa. And in this case, all right, with both angles being 45 degrees, it doesn't actually matter which one we start with. So if this is our angle theta that we're starting with, all right, opposite 1 over hypotenuse root 2. Adjacent 1 over hypotenuse root 2, and opposite over adjacent 1. And this is the most common, all right, pi over 4, aka 45 degrees, all right, is the most common angle that we see in occurrence. And then we also saw last time that we have all those reciprocal angles, right? And we usually line them up just like this. Sine and its reciprocal cosecant. Cosine, its reciprocal secant. tangent is reciprocal cotangent, which means all we have to do is flip. But once you get that SOHCAHTOA and then all the other angles, easy peasy, flip them over. As we just discussed, the other most common triangle is an equilateral triangle. All right, and so along those lines as well, if the inside of a triangle is 180 degrees and I have an equilateral triangle making all sides the same and hence all angles the same, each angle is what measurement? 60 degrees. 60 degrees, aka pi over 3. So all these angles are the same, right? And remembering some geometry notation, right? When you have the line and the congruent, I was like, now what I'm going to do is I'm going to split this right down the middle, all right? A bilateral split, because with 60 degrees, I don't have any right triangles. And for trigonometric functions, I need a right triangle. That then creates a new triangle that has a right angle here. This is 60 degrees. And if I split that top angle, that becomes 30 degrees. So I have, again, 60, 30, 90, which is, of course, 180. And then my sides, all right? So the hypotenuse was 2, all right? I split that side, so it was a bilateral perfect split, which makes that 1. And then I can solve again using Pythagorean theorem to find the missing angle. All right, 2 squared equals 1 squared plus, all right, we're going to do it both ways. If we're doing 60, that means that is the opposite. O squared. 4, 1, root 3 equals our O. And so the other two most common angles, so 45 degrees is our most common angle that we see. The other two angles we see are 60 and 30, right? Pi over 3, pi over 4, pi over 6. And once again, I could pick either one and we could find it because I have my triangle created, right? But for this situation, let's actually look at pi over 3, right? And in which pi over 3 is 60 degrees. So meaning this is my angle theta, right? When I identify my SOHCAHTOA. So SOHCAHTOA. And then so for pi over 3, all right, opposite over hypotenuse. Adjacent over hypotenuse and opposite over adjacent. And then for all the reciprocals, flip them. And now, again, like I said last time, I tend not to bother rationalizing those square roots, but you'll notice that in the solutions, and again, my math lab in particular, you have to rationalize, all right? But it's a one-step algebra solve. So you should be aware how to rationalize, but I'm perfectly fine you leaving the solutions not rationalized because this is still a number. It doesn't really matter. Not the point, right? We're all about, we want to find the concept that matters. And that's just as exact as saying root 3 over 3. Same difference. What that leads to, all right, are the most common angles. And that cheat sheet that I gave you the first day, this has them on that cheat sheet on the unit circle in the top right. And yeah, it's specifically even, that's just these, all right, in that first quadrant, 30, 45, and 60. Now, the best part of this is we use these so much, but since tangent is a function of sine and cosine, right? Tangent is sine over cosine. I don't even need the TOA part, right? All you ever need is to know sine and cosine for particular angles, and you can find the remaining 4. Because the rest of these are all combinations of sine and cosine. It all starts with sine and cosine. And here's the other part. Notice the symmetry. All right, 45 is root 2 over 2, aka 1 over root 2. Sine of pi over 6 is 1/2. Cosine of pi over 3 is 1/2. Sine or cosine of pi over 6 is root 3 over 2. Sine of pi over 3. So it's because it's the same triangle, you just flip it up. So I mean, these are basically all the same. And I put emphasis on this because I know you have a cheat sheet. But if you're definitely going further in math, we just come back to these over and over and over again. And being able to pull these out immediately is going to be really, really helpful to you. Or every time you can draw these triangles. I mean, these triangles are not complicated. Again, it's based on 2 of the 3 most important triangles that exist: isosceles, scalene, and equilateral. And I mean, I could draw these triangles and I could figure those out every single time with no knowledge. So again, you have a cheat sheet, but the more familiar you get with these, the more you want to just spit them out. Oh, calculator. Okay, so, all right, and I can't do the calculator, I apologize, on the iPad. But general thing, all right, look at your calculator. The button next to the second, right, is the mode button. And you notice that down a little bit, you have the option where it says radian or degree, okay? You making sure that you're in the right measurement is super important depending upon what the setup is, all right? Your calculator is going to help you out finding some easy ones. Now, pi over 4 and sine of pi over 4 and sine of 45 degrees, we just talked about it. Those are exact values. Whenever possible, we want to be exact. But when you start getting imperfect values, all right, make sure you're looking at the context as we're going to see in this next problem. Make sure you can switch between modes and degrees. So let's just practice. All right, so I'm currently in radians. So sine of pi over 4, and the pi button, in case you didn't know, is the caret button right above the division sign. Second pi divided by 4, and gets us our approximate value of 0.707. All right, so we're going to be exact as often as possible, but we can't be exact quite all the time. And we're going to see in the next problem that we need to use our calculator, and it is a nice option. But the biggest issue I always saw is people are like, they're doing the problems, they're like, oh my God, I've done this 10 times, I can't get it right. What mode were you in? The problem was all about degrees and they were still in radians, or vice versa. So biggest thing, always check what mode you're in. And it is literally as fast as hitting that button, but it can be the most frustrating thing, right? And I still do it. I was like, solve problem 5 times. I'm like, I just can't get the right answer. And I'm like, let me check my mode. Oh my God. So, all right. Okay, so let's look at an example. So trig is not just wonderful, beautiful mathematical theory. It is actually solid physical application of scenarios. So a surveyor can measure the width of a river by setting up a transit, an instrument that measures angles, right, at a point C on one side of a river, and then taking a sighting on A, the far side of a river, right? After turning 90 degrees, all right, after turning through the angle of 90 degrees at C, the surveyor walks 200 meters to a third point, all right, using transit B, measures the angle to B, 20 degrees. What is the width? What is the width of the river? Okay, so we start out, all right, and a transit, it's like on a tripod, kind of looks like this, right? The guy looks through it. All right. So he starts out at point C. All right. He's measuring a point on the other side of the river, which we are calling point A. And so in here we have our river. Turning 90 degrees, walks through at C. Okay. Then he walks 200 meters, all right, to the same side of the river again. All right, we're going to call that B. And that gave us this distance. Because the whole idea is that, all right, we can't get to the other side of the river. So we're trying to measure, all right, the river. And my picture's not perfect to scale here. All right. And, oh, sorry, he measured far side, actually it makes more sense, he would measure this, that's me. All right, so he measured, okay, 90 degrees, oh, I see. Hmm. Okay, the surveyor walks 200 meters to a third point, turns 90 degrees, so he made our right angle, and then found a point over here. Then he measured the angle B, all right, measuring back to angle point A. We found that to be 20 degrees. And so with that information, all right, we can identify the width of the river. Specifically, we are looking for, what is this? All right, what is this distance over here? All right, because that's going to be the width of the river. And so if I know, all right, this side down here, all right, I'm looking for that opposite side in red, all right, what trigonometric function relates an angle, an adjacent side, and an opposite side? Yeah, TOA, opposite, adjacent. So I can relate this with tangent, and that's all this ever is. All right, again, my picture looks like messing up. Looks bad. But tangent of 20 degrees equals opposite, I might just call that O, all right, all over 200. Just so it's not zero, opposite. In order to solve this, multiply the 200, and so let's get close. X equals 200 tangent of 20 degrees. Multiply 200, and the math, the algebra here is very, very simple. And tangent of 20 degrees is one that we do not have an exact value for. All right, so I'm going to go back to my mode, make sure it's in degrees. 200 tangent, and the tangent function, right? You see sine, cosine, and tangent are all under calculated there, right? One row above 7, 8, and 9. So tangent of 20, and you should get 72.79. All right, is everyone okay on their calculators there? Very nice. And then one other thing, what else do I need on this? Meters, units, all right? That old phrase, if you start in words, you end in words, all right? Make sure you have your units, all right? We are going to do lots of pretty math without that is unitless. When we have context, make sure you have your units, all right? That's the biggest thing that we need to do. But the calculation is always about this simple. And I mean, this is the level that Trig is used most commonly. It's not hard math, but it's very, very applicable. All right. All right, and was everyone okay? Is everyone okay with the calculator? All right, we good, we good, we good. Make sure, Catherine, you good? Just want to make sure everyone. It is not difficult. Just make sure that we're all on the same page there. Okay, so along those lines, all right, we can extend the definition of the trigonometric functions, and this actually comes back around to the unit circle. All right, for any distance, all right, which we're going to call R, which always becomes our hypotenuse, right? By definition, R equals the square root of A squared plus B squared, all right? So instead of calling that C, I'm going to call that R, meaning that that is any, all right, picture that we look at. And what we're going to be able to generalize this to any point, A comma B, all right, in the universe, where this distance, all right, out to that point is always what we are titling as R. AKA R radius, all right? And this is how that circle is drawn, all right? That is the unit circle. And so along those lines, SOHCAHTOA extends, right? Instead of calling the B opposite, I call it actually the point B. It always refers to the Y value. Cosine always refers to the X value, and R will always be our radius. And all those trigonometric functions then go from there. This then allows us that anywhere we go, right, we always start at the origin, and I can find the trigonometric functions with just simply now a point. All right, so I have the point 4, -3, which is down here. And you create your triangle on the x-axis always. So I have some angle theta, all right? Our point pair is x comma y. So the x distance is 4. The y distance then is -3. And I can solve for r. 16, 9, 25, 5. And oh, look, it's our most famous triangle. It is a 3, 4, 5 triangle. And this is always the better way. So those other additional formulas, right? Sine is B over R, cosine is A over R, tangent is B over A. I was like, I don't use those, all right? What we do always is plot your point, fill out your triangle, and then go back to SOHCAHTOA, right? Those are specialized versions of the same thing. It always can break back down to SOHCAHTOA. All right, so opposite over hypotenuse. Adjacent over hypotenuse. Opposite over adjacent. And the corresponding reciprocals. Now, here's the big thing, and this is what we want to make sure we notice. That we have negatives and positives in here, okay? So this is actually even more useful because we actually have a direction. We're dealing with vectors, all right? We actually can identify a direction with this point instead of just always a triangle in essentially the first quadrant. We can actually go to all 4 quadrants now. And this is also what I was talking about. Sine is always going to basically refer to the y's. Sine refers to the y's, cosine refers to the x's. And this identifies what is positive and what is negative, right? Given that I'm in quadrant 4, okay, x is still positive, y is negative, and hence that's why sine is negative, cosine is positive. Tangent is sine over cosine. So if you have a negative divided by a positive or a positive divided by a negative, tangent will be negative, all right? And this allows us even more of these relationships between our trigonometric functions. Coterminal angles always, and the coterminal and reference angles are basically the same thing. Coterminal, all right, angles and reference angles, all right, which I have down here. It basically says, however many times you're spinning around through the origin or through the positive x-axis, however many times you're spinning back around, subtract that off until you get down to an angle that is basically 0 to 90. Because 0 to 90s are the ones that we're going to know, right? And specifically 30, 45, and 60. Those are always going to be the angles that you're trying to create. Because you could spin around, the equivalent of 45 degrees is the same as 405 degrees and whatever 360 plus that again, all right? So however many times you keep going around, all right, it just cut it off until you get down to an angle you actually recognize. And so along those lines. So I have sine of 390 degrees. I want to find the exact value, and I can. Because I basically say sine of 390 degrees is really sine of 360 plus 30, which is still the same as sine of 30 degrees. It doesn't matter, all right, how many times you spin around, it still boils down to just that angle. And this is now one of the ones that sine of 30 degrees, that is one of the ones we found on that equilateral triangle, which is 1/2. And again, all right, you'll get more familiar with those, but for now, just look at your cheat sheet. What's sine of 30? Oh, there it is. Similarly, secant of negative 7 pi over 4. All right, so that's one where I kind of need to think about what that one looks like. Okay, first of all, actually, before I draw it, I can identify secant. I have no idea what any secants are. Well, what does secant relate to?
Cosine.
Cosine. What I do know is cosine. Cosine of negative 7 pi over 4. Okay, there's something I can actually find. And 390 is an easy one, but 7 pi over 4, I might need to think about this one. So let's see. Negative, all right, negative 7 pi over 4 is also important because negative means which direction am I going? Yeah, I'm going down, aka clockwise, not counterclockwise, which is how our quadrants are laid out. All right, so negative 7 pi over 4, okay? So how far is 180? How many radians is that? Pi, okay? And that's bigger than that, okay? So I'm definitely at least this far, all right? And then pi plus pi over 4 is how much? Sorry, pi plus pi over 2, aka 90, is how much? See the math we have to do? So pi plus pi over 2, aka 1 plus 1/2. Do we need to write it?
270 degrees.
Oh, 270 degrees. Okay, let's stick in radians though. 270 degrees, aka 3 pi over 2. So 3 pi over 2 puts me here. And then I say, is 3 pi over 2, is 7 pi over 4 or 3 pi over 2 bigger? AKA 6 pi over 4, 7 pi over 4. Which means I'm actually past 3 pi over 2, aka 270, right? We're still practicing, which means I'm actually, oh look, I'm all the way back in the first quadrant. Specifically, I'm pi over 4 past. Negative 7 pi over 4 is actually the equivalent of positive pi over 4. And yes, dealing with the radians, all right, takes practice, and that's why I want us to make sure we keep looking at that. How far is each one? All right, and this one was negative, so it had an extra little fun twist to it. All right, so the equivalent of negative 7 pi over 4 is actually exactly the same as positive pi over 4. So even though I went the negative direction, I ended up back exactly where I was looking. Now, here's the other way. A lot of times, drop that pi, 7/4. 7/4 plus 1/4 is 2. And remember, all the way around is 2 pies, aka I could have done this a lot faster, but I wanted us to think as we go all the way around. All right. So that's the quick way. But I was like, we deal with so many fractions, and the pi in there throws everyone off, right? It's 7 pi over 4. Don't forget, it's just 3/2. It's just 7/4 and a pi, right? So think about the fraction, right? Because this is 1 1.5, 2, right? Half, 1, 1.5, 2, right? I had the pies in there because that's the measurement. But I was like, we get so caught up with the pie that I see everyone and they're like, oh my God, I don't know what is the pie? It's just a fraction, right? So don't panic over that part. And practice helps you ignore that, definitely. So cosine pi over 4, which is one I know. That's 1 over root 2. 1 over root 2 is just root. And so the point is that something that looked very complicated initially, super easy. But we used a lot of different things there. We used reciprocal angles, we used a negative angle, we used then reference angles, aka coterminal, and then we used our isosceles triangle in order to find the exact value. So we are able to do a lot. This then comes back to what I was talking about with the actual quadrants. All right, this also helps me identify at the end, making sure my sign is correct. And it always comes back to exactly what I just said, that sine is y and cosine is x. So in order to identify, all right, now I have the whole thing written out, but we can do it with just x's and y's. In quadrant 1, is x positive? Is y positive? Yeah. And then, is a positive divided by a positive positive? Which means in this one, all trig functions are positive. And we can do it as we go around. All right, so in quadrant 2, all right, is sine positive? Sine is y. Is y positive here? Sorry, I said sine instead of y. Y is positive here. Is x positive? No. All right, which means, all right, cosine is negative, and then remember, sine divided by cosine, a positive divided by a negative is a negative, which means the only thing here, all right, sine and its reciprocal, cosecant, they're actually the only ones that are positive here. And similarly, we can keep going, all right? Sine is negative here, cosine is negative, both x and y, but this is actually the situation. A negative divided by a negative is positive, which means tangent and its reciprocal are the only things that are positive here. And lastly, similarly, cosine and its reciprocal secant are the only things that are positive here. Now you can always write those out, and again, that's something else to put on a cheat sheet, but it's always just x and y, right? If you remember that y relates to sine, x relates to cosine, and tangent is sine divided by cosine, you can always identify the proper sign of the trigonometric function. All right, so back to reference angles, coterminal angles, basically synonyms. Identify the reference angle wherever you are, and then use that concept of what is positive and negative, depending upon the trigonometric function, x and y, all right, to determine its exact value and then the sign associated. Now, both things we looked at in this one, we didn't have to worry about the sign because they both ended up in quadrant 1. And in quadrant 1, right, 30 degrees and 45 degrees are all positive. Down here, we want to make sure we graph it out, draw a picture. Every time, pictures are worth 1,000 words. And then identify what is positive and what's negative, and the smallest acute angle you can identify. All right, so 135 degrees, we're going to start with something we're familiar with. 135 degrees is in what quadrant?
Second quadrant.
Second quadrant, right? When we're in degrees, yeah, you were fast on that, right? When we're in degrees, we're just so much more familiar. So it's somewhere over here. All right, and I want my reference angle. Always, a reference angle is an angle off of the x-axis. All right, the acute angle off of the x-axis. So if that's 135 degrees, what's left?
45.
Oh, and is that one of our good angles? The good news is I guarantee it's going to be 30, 60, or 45. We only have 3. All right, we're going to see a way that we're going to have more, but those are all we have at the moment. That's 45 degrees. All right, so sine of 135 degrees actually equals sine of 45 degrees, right? And then is sine positive in quadrant 2? Yeah, because sine is y is positive then, which means 1 over root 2. All right, cosine 600. And so 600 degrees, that's something where I definitely want to pull out 360. Because that's definitely going around more than once. So that gives me cosine of 240 degrees, which I know that is equivalent. I circled around. And then 240 degrees is in what quadrant?
Third.
3. Yep. You know, we are, right? And I want us to become that fast with radians, right? You guys are on it with degrees, and that's everyone. Everyone starts, we're just so familiar with degrees. So that's 240 degrees, but I want this reference angle, all right? So what is that angle, all right? That is, in order to find that, I need to subtract off what number?
180.
180. Yep, so 240 minus 180 becomes 60. And oh, look, it's another angle that we're familiar with. And in quadrant 3 that I just asked, is cosine positive or negative? Negative, because cosine is x, and x is negative right there, which means that cosine of 240 actually becomes negative cosine of 60 degrees. All right, but notice that we pulled off 360, we got down to 240, we pulled off another 180, and then had to adjust the sine. And this is what we do every single time. You can get any angle as long as it ends up being 30, 60, or 45. But the good news is a lot of angles fall down to those 3. And then cosine of 60 degrees is actually 1/2. So becomes negative 1/2. Beautiful. All right, cosine 17 pi over 6. All right, so now we got some radians. Here we go. Seventeen 6 pi 17. Okay, so always the first thing is pull off if we rotate it around. So this, and I see this initially, this helps people. So 17 divided by 6, right, actually gets me 2.83. So it can be helpful just to get an idea. So that means 2.83 pi. Did I circle? Did I go all the way around once? Yeah, because how far is all the way around in radians?
2 pi.
2 pi. So if I have a number over 2, I need to cut that off. All right, and 2 pi, all right, in 6 is 12 pi over 6. All right, you guys with me? Just to further emphasize this, which means this was 5 over 6 pi. So I just dumped it off a last time, but just to get familiar with the radians, that is a 1 full rotation, which just leaves me with cosine 5 pi over 6. And then again, the fraction, 5/6, 0.83. How far around is that? In what quadrant are we in?
Second quadrant.
Second quadrant. It's not quite 1. Remember, if it's less than 1, all right, then I'm in either quadrant 1 or 2, and that's over 1/2. That's between 1/2 and 1, puts me in quadrant 2. And this angle is 5 pi over 6. And my reference angle, how much is left to make 1. 5/6 plus what makes 1?
6.
1/6, aka pi over 6. And pi over 6 radians is equivalent to our degrees. How many degrees is pi over 6? Because we want to keep going back and forth.
30.
30 degrees. All right. And then, my sign. Is cosine positive or negative in quadrant 2?
Negative.
Negative. Okay, so sine, and then cosine pi over 6 is √3/2. And again, I'm just looking at the cheat sheet, but I just know it really, really well. Because those sine and cosine for those 3 angles, we do them so much, you guys will memorize them too. All right. Okay, and one more, tangent negative pi over 3. And pi over 3 is actually an angle we're familiar with, but negative pi over 3, just always to practice, all right? That means that we're actually going in the opposite direction. And that just goes down to quadrant 4. So tangent of negative pi over 3 actually becomes tangent of pi over 3, and then is tangent positive or negative in quadrant 4. So tangent is sine divided by cosine. So is cosine positive here? Is x positive here? Yes. Is sine positive here? So a negative divided by a positive is a negative. And that's all really the point of that one is. All right, tangent of pi over 3. And that's actually one I don't know because it's actually, but sine of pi over 3 divided by cosine of pi over 3. So sine of pi over 3 is √3/2. Cosine is 1/2, which makes this negative √3. Are you right? So are you seeing the shortcut on the circle here? So actually negative pi over 3, which would actually be this guy, right? So negative pi over 3 is actually equivalent to 5 pi over 3. Y and sine is y divided by x, so it's not divided by that. That's how you read that unit circle. Do you see what I'm saying? Actually, I should just bring it up because I have it. Okay, so the unit circle here, how you read this. All right, so our main ones, all right, 4 pi over 6, x, that means this is cosine of pi over 6 equals √3/2. Sine of pi over 6 is 1/2, right? Cosine of pi over 4 is √2/2. So it's x comma y is how this is always read. And this is just a really, really nice identifier. And this has all the angles. Now, here's the big thing. These ones are all just repeated, right? Just notice the only difference is negatives and positives, all right? Dependent upon sine and cosine being positive or negative. All you actually need is the first quadrant of our main 3 angles. Everything else is a reference angle. Now, we want to get familiar with these angles just so you know all the way around, right? Everyone can say 210, right? But you want to make sure you can also say 7 pi over 6, right? Just how far off it is. Now, I know that that's just pi over 6 off of 180, all right? But that's how you read this unit circle. And this is by far the best starting cheat sheet that you can have, right? I mean, what have we done so far? There's SOHCAHTOA, all right? Oh, and this is what we're doing today, all right? There's all our reciprocal angles, all right? There's our quotient, there's our quotient identities. There's our Pythagorean identities. Oh, this is cat, right? This is cat. I was like, look, we've already gotten through like half this cheat sheet, huh? And it's because, all right, we're gonna see more complicated versions of this stuff. But this is the base function of almost all of this. I mean, we're gonna keep coming back to this over and over again. All right, are we okay with this? This is really a nice like cheat sheet, and it's basically the standard cheat sheet that's in almost all like calc books. Okay, so furthermore, all right, and trig is always this little math puzzle of how little info can we get and find everything else. So if we're told tangent of theta equals -4 and sine is negative, I want to find the exact value of the trigonometric functions. Okay, so tangent is negative. If tangent is negative, what two possible quadrants am I in? Which one?
You're in either quadrant 3.
I could be in quadrant 3. I could be down here.
Quadrant
Wait. I'm in quadrant 3.
2 and 4.
2 and 4, yeah. That's actually, yeah. So I could be in quadrant 2, or I could be in quadrant 4, right? Just knowing tangent is negative, because everything is positive in quadrant 1, and tangent is positive down here because negative divided by negative is positive. All right, then, all right, so that was red. Sine is negative. Where is sine negative? So sine is easier because sine is just y. So where's y negative? What is it? 3 and 4. Did you say 3 and 4? Okay. So I could be here, I could be here. Oh, gee, what quadrant are we in? We're in quadrant 4. Oh, is that what you were saying?
Yeah.
Yeah, so I'm in quadrant 4. So from here, I can draw a triangle. Tangent is then opposite over adjacent. Okay, now I just wrote the values. Tangent equals opposite over adjacent, which is 4, 1. All right, and I didn't include the sign because that sign could be in the numerator or the denominator. All right, but given that I know where I am, which is the 1 or the 4 negative?
1.
The 4 is negative, right? And then, all right, I could use that information to then find my hypotenuse. 1 squared plus -4 squared equals h squared. So what are we at? 16, 17? And here's the good news, okay? X and Y are positive or negative. The hypotenuse is always positive, all right? Because it's going to represent the distance, all right? And that distance, by definition, a distance is always positive. So both of these can be negative, or one can be negative, or neither can be negative, but the hypotenuse will always be the positive value. Because technically, when I take a square root, how many answers do I get? 2. I get, right? Square root of 4 is +2 or -2. Right? But the good news, because of the context that we will always be dealing with in trig, all right, the hypotenuse always represents a distance and hence is always positive. And then once I have that, I can then find all my remaining trigonometric functions. And of course, the reciprocal of cotangent, that's the easiest one. And the rest of them, I just need to use my triangle. opposite over hypotenuse, adjacent over hypotenuse, and flip. And then always give it the double check, right? We were in quadrant 4. Is sine supposed to be negative in quadrant 4? Yeah, because sine is y. Is cosine supposed to be positive? Yeah. All right, and tangent is negative. Okay, it looks good. All right, so you always want to make sure your signs lined up. But basically, it always comes down to use your info, identify what quadrant you're in, make your triangle. All right, and Pythagorean theorem, I mean, we just keep coming back and using it, and then everything is SOHCAHTOA. Pythagorean theorem, SOHCAHTOA. I mean, trig is really actually not that complicated. We're going to see all these little relationships, okay? But it's still the basic concept. Trig is about triangles. Make a triangle. Don't skip that super easy step of making a triangle. All right?
Did you determine that side was 1?
Because -4. I want to, by definition, SOHCAHTOA. They're all fractions. How do you turn an integer into a fraction?
Okay.
I put it over 1. Yeah, and it always works like that.
Okay.
All right. So yeah, that I turn my integers into fractions because everything we deal with is fractions. And yes, that is an excellent question. Thank you. All right, good stuff. All right. So you should now have all the information to do both activities. All right. There's some good problems here. All right, we're gonna start the lecture for chapter 5, part 2 next time. But we got 20 minutes, so if you have any questions, otherwise, you guys have yourselves a good day. Abel, do you have any questions? Are you all right? Take that as a yes.